everyone, my name is Claire Brantley and I will be discussing magnetic levitation. Magnetic levitation is a method by which an object is suspended with no support other than the magnetic field. Magnetic force is used to counteract the effects of the gravitational acceleration and any other outside forces. Magnetic levitation can be used in many transport areas. The transport methods that use magnetic levitation move the vehicles along a guided track without making contact with the ground. The magnets are used to create both lift and propulsion, thereby reducing friction and allowing very high speeds. In itself, maglev technology includes no moving parts. This system can be used with trains, ropeless elevators, and many other modes of transportation. This system is very unstable. There are many effects from wind and gravity and the magnet itself. Therefore, for my project, I will be investigating which controller is ideal for a ball elevated by magnets. I will investigate the PD, the PI, and the PID controllers. Modeling the system. As mentioned before, the concept behind magnetic suspension is to use the magnetic force generated by the electromagnet to counteract the effect of gravity on the ball. Hence, we want these two forces to be balanced. When these two forces are balanced, there is an equilibrium point. In order to solve this control problem, we must first linearize the system along the equilibrium or at the operation points. In order to linearize the system, a first-order Taylor series expansion is used. This will also approximate the behavior of the system. A free body diagram of the system is shown in Figure 1. After analyzing the free body diagram of the system, we can find the equilibrium points by balancing the forces in the vertical direction. The magnetic ball suspension system can be categorized into two systems, a mechanical system and an electrical system. The sum of the forces in the vertical direction leads to the equations listed below, with m being the mass, x the direction of the ball, g the gravity, f the force. B is the voltage, I is the current, R is resistance, and L is the inductance. The inductance of the coil changes with the change in position of the ball, so the inductance of the coil is dependent on the position of the ball. The formula for the inductance is listed below. The magnetic energy of the coil is listed in the equation below. The electromagnetic levitation force can be determined using the theorems of generalized forces. By substituting the magnetic force from the equation before, we can get the final nonlinear equation. The nonlinear term is dependent on the air gap. Thus, we need to linearize the system about these two variables by taking a first-order Taylor series expansion about the points that describe a desired operating point, and small deviations from I and x. In the final first-order approximation, the bar denotes the equilibrium operating point and the tilde represents the small deviations from the operating point. Continuing to solve for the Taylor series expansion leads to the values of x and I listed below. The values for x and I are set as k1 and k2 respectively. In order for the magnetic ball to reach an equilibrium point at 0, the equations for mg and ci over x squared need to be equal to each other. This leads to our final differential equation listed below. By subbing in x of s for x tilde, and x of s squared for x double prime, and I of s for I, we lead to the transfer function shown at the bottom. In addition to the transfer function, I needed to add two additional gains, k-amp and k-sense. K-amp represents the current through the coil that is produced. The sensor is needed to monitor the system. The final open-loop transfer function is shown below. The system is currently unstable because of the pole located in the right-hand side of the plane. The controller needs to move the unstable pole to the left side of the plane. The pole is currently located at negative 18.138 and positive 18.138. Throughout the presentation, I will use variable representation in order to keep the math looking neat. These are the values that I will use for the parameters, with m being the mass of the ball, x the equilibrium position of the ball, I the current, c is a force constant, k1 is a constant that is calculated from the previous formulas, and k2, same thing. The k sensor and the k amp are values that I chose arbitrarily. This plot demonstrates the instability of the current open-loop transfer function. As you can see, the transfer function oscillates continuously, and there is no bounded output and bounded input. The effect of the right-hand pole is making the system unstable. The proportional term produces an output that is proportional to the current error value. A high proportional gain, in general, results in a large change in the output for a given change in the error. If the high proportional gain is too high, the system can become unstable. In contrast, a small gain results in a small output response to a large input error, and a less responsive or less sensitive controller. If the proportional gain is too low, the controller action may be too small when responding to system disturbances. For my system, I am unable to use the proportional gain because the Kp does not contain an S component. Therefore, this will not be able to bring the pole from the right hand to the left hand side. This is an explanation of how the proportional controller works. In the case of the maglev, if the distance of the ball increases slightly, the current will increase or decrease proportionally to offset the error, and that is how the proportional controller works. This is a model that shows the PD controller. The PD controller includes the proportional and the derivative aspects of the PID controller. The derivative process uses the error that is calculated and determines the slope of the error over time, and by multiplying this rate of change by the derivative gain. The derivative controller predicts the system's behavior and improves the settling time and stability of the system. Derivative controllers are not used in practice that often. This is because of the variable impact on the system stability. Shown here is the model of the PD controller. As you see, I have the PD controller in the closed loop portion of the system. Shown on the right-hand side is the full transfer function of this system. For the PD controller, I used arbitrary values for KD and KP. This shows the effects of different values using KD and KP. The PD controller is used in the closed-loop transfer function listed below, and you can see when KD, the derivative value, has a small value, the step response increases, and when KP has a large value, the step response decreases. This is the results from the PD controller when I chose a proportional value of 1.1 and a derivative value of 0.1. As you can see, the value of the step response levels off at about 1.6, and the time it takes to get there is about 0.49 seconds. This is not the most ideal situation since the time is so long. A plot of the root locus is shown on the right-hand side. The PI controller is a combination of proportional and integral. The combination from the integral term is proportional to both the magnitude of the error and the duration of the error. The I value will account for past values in error. The integral term accelerates the movement in the process towards the set point and eliminates the residual steady-state error that occurs with pure proportional controller. However, since the integral term responds to accumulated errors in the past, it can cause the present value to overshoot the set. Here again is a model of the PI controller, and on the right hand side you can see the closed loop transfer function, which includes the PI controller. For the PI controller, I chose the value of Kp equal to 0.1 and Ki equal to 0.1. Again, these values were chosen arbitrarily. The transfer function for this PI closed loop system is shown below. On the left you can see the step response, and on the right the root locus. From initial inspection it may seem that the step response just has a spike and might be stable, but I required further inspection to prove that this system was stable or not. I investigated the Routh-Hurwitz array to see if the PI system was stable. As you can see initially from the array, there is one sign change, meaning that there is a pole in the right-hand plane and the system is not stable. But this Routh-Hurwitz array was a little more complicated. The S2 value in the transfer function is 0. Therefore, that would make the S1 value a non-existent value because 0 would be in the denominator. I had to do some research on how to calculate auxiliary polynomials and what to do when there is a 0 row. On further research, I concluded that by taking the derivative of the value, the transfer function, you can substitute that into the Routh-Hurwitz array and continue. This array proves that the system is not stable. Just to make sure the PI results that I used weren't bad and making the system unstable, I tried large values for Kp and Ki and got very unstable results. The large value of Kp and a small value of Ki also led to an unstable result, shown on the left. I tried a different combination of small values for Kp and small values for Ki, also large value of Ki and a small value for Kp, and I came up with something similar that you saw on the previous slide. Additional values for Kp and Ki are still shown to be unstable. Upon further investigation of my previous plot, if you scrolled over you could see that on the plot it was shown to be very unstable, and it continued like this sine wave until infinity. The PID controller uses all components of PID. It calculates the error continuously. For the PID, I used values chosen by manual tuning. As you can see, there is a model of the PID controller and the transfer function is shown on the right. For the manual tuning, the system was continuously updated. I would first set the values of Ki and Kd to 0. I would increase Kp until the output of the loop oscillates, then Kp was set to approximately half of that value. Then I would increase Ki until the offset was corrected in sufficient time for the process. However, if I increased Ki too much, this would cause instability. Finally, I added Kd, which may or may not have been needed depending on the response that I was looking for. I had to be careful not to add too much to Kd because this would cause excessive overshoot. Shown here is the results of the PID controller. I have a high value of Ki and lower values for Kp. The values for Ki are supposed to increase the overshoot, which is seen, and increase the settling time, which is also shown. Shown on the right is the root locus. Although this does not appear to be the most optimal system, with numerous values of Ki and P, I was able to find many unstable systems. This is one of the few systems that I found that were stable that was the most optimal. In conclusion, the PID controller and the PD controller are the most optimal because they have a final settling point. For my report, I would like to do further research on the effects of sampling, i.e. placing the controller in the z-domain. I was also introduced to a new method of finding the PID controller. I would also like to do further research on the location of the controller. In my presentation, the controller was located in the closed-loop system. I would like to see what the effects are of placing it into the open-loop system. As a final note, I would like to say that all controllers can lead to an unstable output. I had to try numerous values to get to the optimal solutions that I calculated. If you have any questions about my report, feel free to email me at brantley@iastate.edu. Thank you for listening to my presentation. In addition, I have listed the references that I have used throughout this report. Thank you.